So, last class we have discussed the vector and matrix norm of a constant matrix or constant vector norm. The most general P norm is defined like this way, and when we have seen when P is equal to 1, we call it is a L1 norm or 1 norm. This is nothing but a the sum of all elements in the vectors absolute value, sum of all absolute values of these vectors elements. L2 norm is nothing but a the L2 norm when P is equal to 2, P is equal to 2, the L2 norm is nothing but a distance of the vector from the origin. This is also called Euclidean norm. Next we come into when P is equal to infinity, that we will call H infinity what a L infinity norm or simply infinity norm of a vector. That is nothing but a maximum absolute value out of the all elements of the vectors, that is the L infinity norm, simply infinity norm of a vector. And next we came into the picture that a matrix whose elements are constant, then how to find out its different norms and different applications. So, first is Frobenius norm. It is nothing but a that matrix whose Frobenius norm how to compute is nothing but a all column vectors this you put it in sequence. So, that whole thing will come a vector of dimension m into n cross 1. So, find out the what is called the norm 1 of this vector, norm 2 of this vector. So, this is called the Frobenius norm of the matrix. That means, this column, then put below this column, and below this column, and so on. And whatever the you get it vector, that vector will be a dimension m into n into 1, and that vector what is called norm 2 is equal to the is called the Frobenius norm of a matrix. L1 norm of a matrix is nothing but a maximum column sum. So, if you have a m cross n matrix dimension, you have a n columns are there, out of n columns whose absolute value sum of all elements on that particular column you add it, agree, then this will out of all this column which one is maximum, that is called L1 norm. Similarly, L infinity norm is nothing but a the maximum row sum, that means you absolute value of the all row elements you add it, out of this which one is maximum, it is called L infinity norm. Then L2 norm of a matrix is nothing but a what is called maximum eigenvalue of this A transpose A, and this A transpose A is a symmetric matrix, its all eigenvalues are real, and that is a positive semi definite matrix. So, these all eigenvalues will be a positive non negative numbers. So, you out of this which one is maximum, that will give you the L2 norm of a matrix. So, this same idea will now extend for a signals. So, now our question is the signal and system norms. So, in any signal the energy is present when any signal is presented over a interval of time, the energy contained in that signal how we will compute, that we will call the size of a signal or strength of the signal. So, the energy contained or present in a continuous time or discrete time signal over an interval of time is given by so E energy over the interval T1 to T2, T2 is greater than T1 is divided by T 1 integration of T 1 T 2 and x of mod of t square. But mod why I have taken mod, suppose the signal is complex, then you have to take absolute value of that signal. For the time being I am considering it is a scalar signal. So, this dt in the interval t is equal to T 1 comma T 2. How it is energy? Suppose we have a once resistance whose value is 1 ohm, and if I send a current through this one is I. So, what is the power? I square into R, and R is 1. So, simply it is a I square, and I square I is a signal. So, in that case if you consider the x of t is the I, then I square into R, R is we consider 1. So, this is the power then over the interval of this T 1 to T 0 is nothing but a your the energy contained in this signal over the interval T 1 to T 2. This is in case of continuous time session. The equivalent version of discrete time case, the energy present in that interval over the interval, and that in interval in discrete time n 1 comma n 2 and n 2 is greater than n 1 is equal to that integration term will be now replaced by a summation term n 1 to n 2 mod of x of k square. And this is I told you again that absolute value, if it is complex then absolute value is a that meaning. If it is not a real signal is there, then absolute value of this square itself a positive value is this one. So, this now total energy of a continuous time signal, we can write the total energy of a continuous time signal is its energy calculated over the infinite energy calculated over the interval t is equal to minus infinity to plus infinity. So, minus infinity to plus infinity this again. So, continuous time case, now continuous time signal we denote the total energy x over the interval minus infinity to plus infinity. The expression at step only integration limits is changed. So, this infinite the integration minus infinity to infinity, this will be finite provided that x tends to 0 when t tends to infinity. So, this will converge this if x of t tends to 0 as t tends to infinity. So, this energy value will be finite if this condition is satisfied. If this condition is not satisfied, agree, then we have to give some other what we will call meaningful definition of energy size or energy strength. So, we will use the what is called energy the signal strength as a energy when the signal x of t tends to 0 as tends to infinity. So, another the signal which is meaningful when x tends to x does not tends to 0 as t tends to infinity, then we have to use another definition of energy content in that signal, that is called power signal. So, similarly in discrete time case, discrete time signal or sequence, E x is equal to minus of k is equal to minus infinity to plus infinity mod of x of k whole square. So, the signal E is said to be E of x. Suppose you denote this thing is E of x, this thing you denoted by E of x, and this thing also you denoted by E of x. So, the signal E is said to be finite energy whenever E of x less than infinity. So, this will possible if the signal tends to 0 as t tends to infinity. If it is not true, that means x does not tends to 0 as t infinity, then we cannot express the signal as an energy, signal energy. So, we have to convert, we have to give the meaningful definition of power energy, power energy. The definition of power energy is it is defined as energy per unit time. This definition or this meaningful definition will give when the signal does not tends to 0 as tends to infinity. That means, in that situation the definition of energy, power energy will be infinite, and infinite has no meaning of this energy content. So, we will consider in that case is power energy time. So, the by definition this the average power of a continuous time signal x t over the period, over the interval t is equal to minus infinity to plus infinity is given by that E p x, this is for continuous time, p x is equal to limit t tends to infinity 1 by 2 t minus t to t mod of x t whole square d t. And discrete time case p of x is limit k tends to infinity 1 by twice k plus 1 summation of k is equal to minus infinity to plus infinity, or you can say then it is a mod of x k whole square, or you can say this is instead of write it k is equal to capital minus k, capital K, and capital K tends to infinity. In this way, I can write capital K tends to infinity. So, this is capital K. In this way, instead of writing infinity to minus infinity, you can write, because I have written capital K tends to infinity, capital K tends to infinity. So, 1 by 2 k plus 1, because minus k to plus k, that is 2 k, there is a 0 is there in the time index. So, it is a 2 k plus 1. So, this is in the case of discrete time case. So, when we will use the meaningful definition of power energy, when the signal does not tends to 0 as tends to infinity, t tends to infinity, then you will use the meaningful definition of power energy. And energy will use the definition of energy signal. This is the power signal, not power signal. The energy signal definition, when we will use it, when the signal tends to 0 as tends to infinity, then we will use the meaningful definition of energy signal. So, that is next. Now, I will leave in an exercise to show that whether this is a power signal or energy signal. So, I have just discussed first is energy signal. This is the definition of an energy signal, and this is the definition of power signal. And when you will use the definition, meaningful definition of power signal or energy signal, just we have discussed it. Now, we have a what is called continuous time signal. This is the continuous time signal, that x of t is equal to 5 when t is minus 2 and 0 elsewhere. That means, signal, if you see this one, if it is a 1, 2, 3, 1, 2, 3, 0, minus 1, minus 2, minus 3, minus 4, the signal is like this way. This is a 5, 1, 2, 3, 4, 5, let us go, this is 5. So, signal is continuing up to 2 and this is up to 3. After that it is 0. So, here, so t tends to infinity either side, this is 0. So, this is, we will use the definition of what is called the energy signal definition. What is the energy content in the signal? And next time when it is not, that x of t does not tends to 0 as tends to infinity, then we will use the power energy definition. What is the power content in that signal? Average power. So, if you work out this one, then your E x is equal to minus infinity to plus infinity mod of x of t. In this case, since it is a real signal, we need not to take the mod, x t of square is enough. So, this is nothing but a 25 minus infinity to plus infinity, then then d of t, then this is nothing but a 225, if you that limit is really minus 3 to plus 2. So, it is a 2 minus 3 and this will come 5 into 25, 125. So, this is finite. Whereas, power is, as definition of power, t tends to infinity, this will be a 0. In case of average power, this average power is tends to 0, this is 0. So, we have used the signal is energy signal. Now, if you use the what is called another example, you take it. Suppose we have the signal x of t is equal to 10 cos pi by 2 t plus pi by 4. Look, this signal is a periodic signal. And its frequency is, and its frequency is, what is its frequency? Is pi by, let us call this is your omega. Omega is what? Pi by 2 is equal to twice pi f. So, pi cancel, f is equal to 1 by 4, therefore, implies t is equal to 4. Time period is 4. Since it is a periodic, you need not to go do, it is enough to go for integration, average power integration for a one complete cycle. So, our in this case our E of x is equal to if you call E of x minus infinity to plus infinity x of t square dt. And if you just this is the energy signal, if you use it, I told you this does not tends to, this signal does not tends to 0 as t tends to infinity. So, if you apply the energy signal, this value will come, this is a 10, it is a 100 integration minus infinity to infinity, then cos square pi of t plus pi by 4, and this results is infinity, that means infinite energy, signal, which does not have a meaningful definition when I use the energy signal. But if in case of power signal, what we will do it 1 by t to t, or because it is a, I just consider the from 0 to t is defined. If you consider this is defined from t greater than 0 less than infinity, this one. This is defined into this. So, it is the periodic nature of that one. So, this value if you just calculate this one 0 to t, then cos square pi by 2 t plus pi by 4 dt. Actually, by definition it should be what? If you see by definition, okay, I write it by definition, t tends to infinity 2 t minus t 2 plus t. So, I need not to go for, since it is a periodic signal, agree. So, you take the complete one cycle. So, complete one cycle, if you take it, it is nothing but a 0 to t 1 by t cos square pi by 2 t and pi by d dt, and this value you will get it, that value you will get it, if it is a, after that you will get it, this value is 50 unit. This is cos square, you just convert it, cos square is 1 minus 1 plus, that means this formula use it, that cos 2 alpha is equal to cos square alpha minus sin square alpha, agree. So, twice of this one, that means 1 plus cos twice alpha by 2, that you convert into a 1 plus cos 2 alpha by 2 and then integrate, you will get 15 unit, check, agree. So, this community, even if you do not consider that it is just defined from minus infinity to plus infinity, then this is the power signal. What is the power contents in that signal we have to express, but you cannot express it what is the energy content in that signal, because this become infinite, it is no meaningful of that one. So, next is straightway we will come to the system norm. You have, if you have a system, signal norm of a system, signal norm of a system. Now, we are coming to the system. Suppose we have seen earlier our lecture that if you have a dynamic system is there, we can form, we can write the dynamic equation either in different model, either transfer function model or state space model. Let us call, we have converted, we have a system which is a transfer function model, GS input, and our GS is the transfer function and this is our input u of t, and if you consider in Laplace transform, this is u of s. This is the input of, this is the output is y of t, this is output, and in Laplace domain it is y of s, the Laplace transform of y of t. Now, this signal and output is y of t. This two signal norm of a system, what does it mean? So, signal norm of a systems are usually, just now I mentioned that we can describe this thing in the two model, either transfer function model or state machine model. If you do any model, first you have to write the differential equation based on the physical laws of the systems. Once you write the differential equation, then our job is to convert either in transfer function model or state space model. Okay. So, if it is a state space model, that nth order differential equation you have to convert into n first order differential equation. If you convert into a transfer function model, then you take the Laplace transform both sides by assuming all initial conditions are 0. So, the system are usually described by differential equation. That contains signals x, let us call u of t, over the period of time, over a certain interval of time with varying amplitude. So, our job is to find out the signal is measured by a number. Our job is to measure the strength of the signal by a number, okay, or size of the signal by a number u of t, you know, u of t or y of t or y of t. Strength of the signal or size of the signal or strength of the signal we have to find out. And let us call the signal, if it is a scalar signal, let us call u of t, let us call u of t or y of t, that we denoted by in u of t or y of t we are denoted by x of t. U of t or y of t, let it is denoted by x of t. So, the signal now onwards I am writing x of t. Now, the signal, if it is a scalar, this is a scalar, and that means one signal is there and in real, or it can be x of t can be a vector n cross 1 and vector, this is a vector of dimension n cross, vector of dimension n cross 1. And we assume the signal x or scalar or x t vector are continuous piecewise. These and these are continuous piecewise, or you can say piecewise continuous. This is assumption is made. Now, we will find the strength of the signal as we did it for constant vector or constant vector of dimension n. So, vector case, let us call instead a vector case, or you first use scalar case, scalar signal. P norm, just like is a norm of x of t p. This general definition is that minus infinity to plus infinity norm of x of t, that 1 by p p. Okay. This is the signal curve for this and P is greater than equal to 1, greater than equal to 1 or less than infinity. This is the integer. So, L 1 norm in signal case, or we can show simply one norm is x of t, this is infinity minus infinity to plus infinity x of t dt. So, this signal must be integrable over the period of minus infinity to minus infinity. The absolute value of this signal must be integrable. So, this the absolute value, this is the absolute value of x of t. Now, L 2 norm simply we call 2 norm is so what is the physical significance of this one? It is the energy. This is the energy content, because if you consider a resistance of unit resistance and passing a current x of t, then I square r into I square into r is the power over the interval, this energy. So, this is the representation of energy content in the signal, that provided x tends to 0 as t tends to infinity, then we will consider the energy content in the signal this way. And next is L infinity norm, or is simply called infinity norm. So, that denoted by x of t infinity, and that is defined as supremum T r. What does it mean, infinity norm of a signal? You see, this absolute value I told you, if it is a complex signal, then only you need absolute value. Agree? Here, because signal may be plus minus, and that obviously you have to take the absolute value of this one, whether it is real or complex, this one. So, what does it mean, this one? So, if you plot x versus the time, at what time you will get the maximum value of this one, that means it will always x value will be less than that maximum value, always it cannot cross that value. So, supremum name is the least upper bound, the least upper bound, or it is called the tightest, or it is called, this is also called the tightest possible upper bound. What does it mean? Let us take in one example and see. Let us call, we have a signal example. We have a signal, let us call example x of t is equal to 1 minus e to the power of tau t. This signal, you can say you have a simple resistance, you have simple resistance and inductance. Okay, you are excited with a DC voltage, and this is the current which I am considering x of t is the signal, and current flowing through the signal is like this way. Agree? And so, if you plot this one, suppose you can consider voltage signal is 1, this is signal is 1, and the L also 1, then you see this is the nature of this curve, we will get it like this way. Agree? And this is the x of t. Now, you see The maximum value of this one is I cannot say maximum value. Why? Here I can say the least upper bound of this signal is 1, because here you see at this point whatever the value is there 0.8, after some time the value will be greater than 0.8. So, that is also maximum. Again after some time its value is greater. So, this is also. So, we cannot say anything about the maximum value of this one. So, it has a, we can say that this signal supremum value of this signal is 1. Mean least upper bound of this signal is least upper bound. It cannot go beyond that one whenever it is t even greater than this, but all is the tightest possible upper bound. I am telling in before I am tightest bound of upper bound of this signal is 1. Okay, but I cannot say the maximum value of this signal is 1, this one, because at this point if it is a maximum value is 1, after some time the value will change it more than this. So, you cannot say, in this case we will say this is the what is called least upper bound of this one. So, supremum. There is another term is the infimum. Infimum means greatest upper bound. Again, greatest, this is the greatest lower bound. Infimum, greatest lower bound, greatest lower bound. So, let us call, we are considering, because this definition is coming, if you see the L infinity norm of a signal, symbol signal is nothing but a, you draw the signal, let us call this is the signal, and you are telling this is the most upper bound of the signal. That means, least upper bound, that the least upper bound of this signal is that one, that is called supremum of these signals. So, in case of vector signal, so once again I am telling you this one, that infinity norm of a signal is the supremum value, absolute value of the supremum value of this one. Okay. So, this indicates meaning of literal meaning of least upper bound. I am telling in beforehand the least upper bound of this signal is that much. Okay. For this example, least upper bound of this signal, least upper bound of this signal, least upper bound of the signal is 1, or supremum value of the signal is 1. So, vector signal, again vector signal, instead of a scalar, now we have a vector, it has a n components, vector contains n components, and we will just give the definition as it, as this way, p norm, all these things. So, p norm in case of vector is x summation of minus infinity to plus infinity integration minus infinity, sorry, this is the not infinity, this is I tell you this is minus infinity to plus infinity, then signal. Then how many signals we have? N signal, because x is a vector. Suppose x of t is a vector whose dimension is n cross 1. This is a vector whose dimension is n cross 1. So, we will write it that I is equal to 1 to n mod x I of t mod p, agree, whole, that whole thing 1 by p. Okay. So, please p norm of this one whole thing by 1 by p, here missing is 1 by p. P is equal to 1, this is that, p is equal to 2, this is then that, this is a norm of that one. Agree? So, now what does it mean this one for p is equal to greater than equal to less than equal to 1. What does it mean that one? This indicates the absolute value of x, all you take it p is equal I is equal to 1 to n, p let us call p is equal to 1. So, you add it all these thing I is equal to 1 and all, then integrate minus infinity to plus infinity, and this is called the one. If it is one norm, how will you define x of t p is equal to 1 is equal to integration minus infinity to plus infinity summation of I is equal to 1 to n mod of I this. So, this because p is equal to 1, I is equal to 1. So, this is and it is a dt integration of this, agree. This is also dt. So, this is called one norm, but one norm is absolute value of, you just say I is equal to 1, I is equal to 1 absolute value, I x 1 absolute value, agree, over that interval of time, then x of t x 2 I is equal to x of x 2 of t, add all these things, then integrate over the minus infinity to plus infinity, that is called vector. In case of vector, one norm. Now, the most important is L2 norm or L1 norm previously to learn, that is L2 norm, we simply call 2 norm of a vector or signal, 2 norm of a signal, and signal is a vector, vector signal. So, what is this 2 norm? X of 2, this minus infinity to plus infinity, x transpose, this mind is x is a vector, x transpose t, x of t, this dt and whole half. So, what does this mean? Sum, because x is a signal, it has a n components, that means n signals are there, each signal's energy contained in signal and sum each component of the vector energy content, and we are making the sum of this. In other words, it is nothing but a, if you see this one, it is nothing but a the RMS values of a signal. Agree? If you have a more than one signal, let us call it is x is equal to 1, the I square r, agree, over the interval, agree, into r, r is 1, if you can, is nothing but a that your power. So, this is nothing but a, this quantity is nothing but this norm is the root, means root, you see the root, this is going to be root mean square. So, this norm, sum of this norm indicates the sum of energy contains in the vector signal. So, if you expand this one, let us see this one, if you expand this one minus infinity to plus infinity, x transpose, x is a row vector, this is column vector, it is nothing but a x 1 square t plus x 2 square t and dot dot x n square t whole dt, then you are taking the half of that one. So, this each indicates the energy, agree, energy contained in that signal, vector signal. So, next is L2 norm, L infinity norm, or is simply it is called infinity norm of a vector, infinity norm of a vector signal. So, infinity norm of a vector signal is what? Supremum t is greater than equal to 0, max I, then mod I of t this, and I varies from 1 to dot dot n. What does it mean? See, the infinity norm of a vector means that x of t absolute value you vary 1 to n, x 1, x 2 over the period t 0 to t greater than 0. Out of this, which one is the maximum you note down? Then x is equal to 2 over the period 0 to t greater than 0, what is the maximum you note down? In this way, x I is equal to n over the period t greater than 0, you note down the maximum. Out of this, which one is least upper bound, that is will give you the infinity norm of a that signal vector. Agree? So, this has some important concept which will be utilized in case of our system signal signal norm. So, next is norm for norm measure of systems. So, you see this one scalar case when x of t is a scalar, and our norm p norm of a signal is minus infinity to plus infinity absolute value p of that one. But it is a more meaningful when p is equal to 1, this is the absolute value of signal over the period t minus infinity to this value. Main meaningful of this one is for scalar case is this one. That means x square I 3 x square is a signal multiplied by a resistance r is equal to 1. So, it is a power, and I am integrated over that interval minus infinity to plus infinity. So, the energy contained over the period of time this. So, this is energy content in the signal. So, power content in the signal when we will use the expression, if that x of t signal does not tends to 0 as t tends to infinity, then you will use the expression for power energy power signal concept. So, next is that norm of a system, what does it mean? The system norms are actually the input output gains of the system. So, suppose you have a system G s, y of t is the output, u of t is the input. Now, as you know, the frequency response of a system, what we do it, we have a physical systems, the system is excited with a sinusoidal input, agree, keeping its amplitude fixed, we are changing the frequency and see the output, which is also in time domain, the output of signal is also what is called in sinusoidal form, but its magnitude will be different from the input signal and also phase angle will be different. The frequency of input signal output signal is remain same. So, when input is excited with a system, agree, then output it is mapped to another signal. When input is excited with the system sinusoidal input, it is mapped to the another signal. In case of multi input multi output case, that when input is excited with a multi input signal, that signal is mapped into a output with multi output signals. Agree? So, if you see in the frequency response of the, if u e is equal to a sin omega t, then output will be that y of t will be a g j omega mod sin omega t plus phi. Agree? Mod of this one, this is mod of this one sin omega t. So, our gain of this one, the amplitude, input amplitude is A, output amplitude is A into G. So, G W j omega mod is the gain. So, system norm actually are actually nothing but input output gains. So, the now question is, what is the size of a system norm, the size of a system in a transfer function T f transfer function form is usually measured by H 2 and H infinity norm. The size of a system is divided by H 2 and H infinity norm. So, before that I discuss the H 2 H infinity norm, I will discuss that our important theorem, what is called Parse-Walsh theorem. What is that theorem? Let us call, we have a two signals. I want to integrate that two signal from minus infinity to plus infinity. We have a two signals x of t, another signal is y of t, and we want to integrate product of these two signal over the interval. So, let us call x of t is voltage and I of t is the current in a particular branch in a circuit. In a particular branch, the voltage across that branch is x of t and current flowing into this one of these. So, this product of this one is the instantaneous power. So, I am integrating over the minus infinity to plus infinity, it gives the energy. So, I want to compute that one. Let us call this equation is 1. What is the Parse-Walsh theorem tells, that we will see here. So, what we made an assumption of this one, this Laplace transform of voltage and current exist. Laplace transform of both the signals, Laplace transform both the signals exist. That is our assumption. Now, you see this one, y of t, I can write, if the Laplace transform of y of t, y of s, then I can write inverse of that Laplace transform is 0, j is omega to j omega there is omega is infinity, omega tends to infinity. So, I am stated j this is equal to y of s is equal to s of t dt. Note, if Laplace transform of y of s, y of t is equal to y of s, then y of t I can write it is nothing but a y of t, Laplace inverse of that y of t I can write it nothing but a y 2 pi j and minus j infinity to plus j infinity y of s e to the power s t dt. If Laplace transform of y t y s, the inverse of Laplace transform y of t is equal to this. So, that if you express in this is let us call equation number 2. If you express this into a 1 from 1 I is equal to, I am replacing that y of t by this expression, y of t by this expression in equation 1. So, 2 pi j integration minus infinity to plus infinity, then x of t minus j infinity to plus j infinity y of s e to the power of s t dt into ds, ds into s of d. So, by rearranging this j minus j infinity to plus j infinity y of s and minus infinity to plus infinity x of t e to the power of s of t dt. And by definition of Laplace transform, we can write it this equal to this, and we have a left with ds. So, we can write it 1 plus 2 pi j integration of minus j infinity, this is infinity plus j infinity. This we can write y of s into x of minus s into ds. If x and y are the same signal, that means y, if y s is replaced, y of t is replaced by x of t, if x of t, if y of t is equal to x of t, then from this equation from 3 we can write that integration of minus infinity to plus infinity x square of t dt is equal to 1 by twice pi j minus infinity minus j infinity to plus infinity x of s into x of minus s ds. And this is ultimately we can write it this is equal to 2 pi j, j is equal to minus infinity to plus infinity x of j omega x of minus j omega d omega, which is nothing but a twice pi minus infinity to plus infinity. This I can write it mod of this whole square d omega. So, this indicates the energy content in time domain, relation between the energy content in time domain to energy content in frequency domain or frequency description, the same. So, this is nothing but a Fourier transform of that signal x j x omega is nothing but a Fourier transform of that signal. So, we will stop it here. So, we have made a relation that Parseval theorem, this is called Parseval theorem, it tells that this theorem relates the time domain energy content in the signal in same as the frequency domain energy content the same signal, energy content in the frequency domain also in the same domain in terms of Fourier transform. So, we will stop it here today.